Okay, ladies and gentlemen, let's come together and have our Bellrock discussion now. I'd like to make sure that you have plenty of time in today's class period after our discussion involving function behavior and how we can use limits to determine function behavior. You're going to have a nice block of time to work on your review assignment. Recall that we have our Unit 2 test, our first 100-point test in Infinite Campus. That'll be for us on A Day, Friday. So this A Day, 9/18, we'll be taking our Unit 2 test, and you will have some structured time in today's class period for you to work on those review problems. Answer keys are posted on Moodle, and so you're expected to be checking your answers as you go along to make sure that you're doing things correctly. And I did put a little kind of event description to go along with the course event Unit 2 test on Moodle. You can check that out under upcoming events, or you can go directly to the course calendar on Moodle. Let's go ahead and take a look then at our Bellrock for today. So I'm going to be asking some of you to share your responses for the whole class. For the limit of g of x as x approaches c to exist, right? What has to be true? And we can write that using proper notation. So what has to be true for the overall limit of g of x as x approaches c to exist? What has to be true? Anna?
The limit of g of x as x approaches c from the left side, and limit of g of x as x approaches c from the right side is equal.
Excellent, well said. Thank you for using the proper notation. So the left-hand limit, right? The left-hand limit has to equal the right-hand limit. And we can write that using the proper notation. Limit of g of x as x approaches c from the left-hand side must be equal to the limit of g of x as x approaches c from the right-hand side. Nice job. Raise your hand if you have the left-hand and the right-hand limits must be equal. Right? That's what we need for the overall. Good job. Thank you. For h to be continuous at x equals a, and I used a different function name here, h. Right, let's go ahead and do that as a limit equation as well. So for h to be continuous at x equals a, right, what must be true? Paul?
The limit of h as x approaches a must exist.
Yes. And?
The limits have to be equal to each other.
The left-hand limits, right, have to be equal to each other for this overall limit to exist, right? So that gives me the left hand and the right hand matching. That's the smooth part, right? That's the smooth part from the left and right hand side. But what about that middle part?
H of a has to be there.
It is right there. It is right there. In fact, it's right here, and it's right next to this limit, right, of h as x approaches a2. And it would just fill in that hole, right? It would fill in that hole if I just put what relational symbol right here.
It has to equal it.
Yes, absolutely. So the limit of h of x as x approaches a must equal the value of the function h at x equals a. This limit doesn't care about the value of the function at x equals a. This is the value of the function at x equals a. We need that overall limit to equal the value of the function at x equals a. Perfect. Wonderful. Thank you, Paul. That's just right. I'm going to, there. As you know, I've been taking some night classes at UW-Baraboo, Sauk County, trying to improve my handwriting, and so I'll be practicing that throughout our class periods here, just trying to, I'm going to do a cursive little took on that h. I better do the same cursive h over there, because it's the same function. All right. The different types of discontinuities, goodness, we've got a lot. And so what's one type of discontinuity? What's one type of discontinuity that we have? Preston? A step discontinuity, right? A step or a jump discontinuity. And we know that that's an instance where the overall limit does not exist. And so if we're considering a step discontinuity, we know the only way to continue along that function would be to lift up your pencil, right, and go to the next level or down to the next level to continue on. In this case, the function could or could not be defined at x equals c. However, we know for sure that the overall limit does not exist because the left-hand limit does not match the right-hand limit. What's a different kind of discontinuity that we've encountered? Jake?
Infinite.
An infinite discontinuity. Thank you. An infinite discontinuity is synonymous with a vertical asymptote, right? That's a vertical asymptote. They mean the same thing. We recognize that as the function values shoot off towards positive or negative infinity as x gets closer and closer, but not equal to some x equals c value. So we've got an infinite discontinuity. And then our final form, Brandon?
Obviously I have no idea for the last discontinuity. A removable discontinuity?
Is correct. A removable discontinuity is I've
Also
heard,
known as a whole.
also known as a whole. A removable discontinuity is a situation where my overall limit does exist as x approaches c. My left-hand limit matches my right-hand limit, and they converge to a single y value. However, the function, right, the function is either undefined at x equals c, or it's defined in the wrong place, so that the whole is an open circle. And so the overall limit does not match the value of the function, which may not exist or may be defined to be somewhere else. We could remove that discontinuity by redefining the function to fill that hole, to plug the hole, and then we'd have all of our pieces together. Nice work. Thank you, you guys. What questions do you have on 1 through 3? All right, and let's get to our algebraic evaluations. Remember, when evaluating a limit algebraically, this would be on the non-calculated portion of the test. We always want to do we always want to do a direct substitution first to see what we're working with. And so upon initial substitution, I get m going to 2 minus 2 is 0, over m going to 2 to the 4th is 16 minus 16 is 0. I get an indeterminate form. And so, more often than not, we found that this limit does exist. This is a situation where the function is not defined at x equals 2, right, or in this case m equals 2, but the left-hand limit, right, matches the right-hand limit. Let's go ahead and see then what the value of the expression is approaching as m approaches 2. So we can go ahead and dig into our algebraic tool bag, though duct taped and tattered worn it may be, and we'll grab onto some algebraic strategies that may be useful in rewriting that expression. So what do we want to try? What do we want to try here? Riley?
Factoring.
Factoring. I'm down with the factoring too, so we'll go ahead and do the limit as m approaches 2 of m minus 2 over, oh goodness gracious. So we've got a whole lot going on here. We could first do, that's still quadratic form, right? We could do m squared plus 4 times m squared minus 4. And then that doesn't help because I still get 2 squared is 4 plus 4 is 8. And then 4 minus 4 is 0. I still get 0 over 0. However, it looks like we can go one step further. Do you guys see that? So it looks like we can do another difference of perfect squares and continue on. Make sure you keep your limit notation throughout until our final direct substitution. I still have m minus 2. On bottom I have m squared plus 4 times, and now we'll break up that difference of perfect squares and squiggle underline red into our product of two binomials in red. It looks like m plus 2 times m minus 2. Did we get it all? And now, because we're evaluating a limit, right? A limit where m does not equal 2, but rather is just approaching, we get to play my favorite game. Yes, that's right, the cancel game. So we can cancel out those factors because m doesn't equal 2 when evaluating this limit. And I get 1 over quantity m squared plus 4 times quantity m plus 2. And we're ready to try again. Is m equals 2 in the domain of this expression now? Michaela?
Yes.
Yes, so we can evaluate through direct substitution, and for the first time, ladies and gentlemen, we can drop our LIM. Make sure you're keeping your limit notation precise and correct throughout until the appropriate time, otherwise you'll lose the notation point on each of these algebraic evaluations, and you don't want to do that. You don't want to miss out on easy points. So this would become 1 over 1 plus 4 is 5 times 1 plus 2, I'm sorry, 2. We say 2 plus, no. 2 in for m would go to 2 squared is 4 plus 4 is 8. Is that what you guys are getting? 8 times 2 plus 2 is 4 is 8 times 4. So goodness, I'm getting 1/32. Raise your hand if you had 1/32. Anybody else get that? You did. Awesome work. Way to go, you guys. Great job. Okay, so as we continue our algebraic evaluation, direct substitution into my number 5 gives me negative 1 cubed. Oh gosh, pesky little buggers, all those negatives. So I'm getting negative 1 minus 4, that square will always be positive, plus 2 plus 3 all over 0. So I get -1 minus 4 is -5 plus 2 plus 3 is 0. So I'm getting 0 over 0. That's an indeterminate form. So what am I going to do? Well, we saw how this typically equals some value, like 1/32, right? In order to get there, though, I've got to be able to rewrite that expression such that my x value of concern is in the domain, so I can do an evaluation through direct substitution. And as I try sorting my factoring, I don't have a difference of perfect squares like last problem, so I can't factor like that. Although we do have other factoring techniques. What technique did we use in advanced algebra when we had a four-term polynomial? Brandon? Grouping, right? We could try factoring by grouping. As I consider breaking this up into two groups, however, the factorization of a GCF from the first group and a GCF from the second group, would that result in a common group produced? No, I'm not seeing that pattern here where I've got 1 and then 4 and then something and then 4 times as much, right? I'm not seeing sort of that pattern where I got a common group. And so yes, factoring by grouping is a strategy I can employ on a four-term polynomial, but only if it results in a common group. And for this, it will not help us. So now's when we quit, right? Now's when we go to Wannable, right? And grab a couple of pitchers of root beer, maybe bowl some, is it called frames? Yeah, bowl some frames, not shoot some frames or something. Games, bowl some games. No, we're gonna stay strong and see if we can't factor this another way. So, what other technique could we try when we've got a non-quadratic, a higher than degree 2 polynomial here? Jake?
Synthetic substitution.
Yeah, we could try synthetic substitution and the rational roots theorem as a means for chunking this down to a lower degree, lower than 3, so that I can factor it using my traditional quadratic factoring techniques. And so, wouldn't it be cool if we had like, oh, I don't know, like a little handsome carrying case that we could use for synthetic substitution? That would be pretty sweet. Yeah, it would, Mr. Fritz. So let's go ahead and try. We'll consider our potential rational roots. If I look at this numerator here, my potential rational roots include the positive and negative quotient of the factors of the last divided by the factors of the first. So the factors of my last are plus and minus 1 and 3 divided by my factors of the first. Leading coefficient is 1, so that's just 1. So it looks like I can try 1, -1, 3, and -3. So I'll go ahead and choose 1 to try. Let's try 1. And we know that I copy my coefficients over for my cubic, so it looks like 1x cubed minus 4x squared minus 2x, and then plus 3. Recall that our synthetic substitution process, Riley?
Well, since we used -1 as since we tried -1 already, can we put that in there instead of 1, since we know that will probably be a factor?
We know that -1 is a 0 of the factor on the bottom, and we're hoping that it's a 0 of the factor on the top.
Well,
So because we already got 0?
yeah, when we found that indeterminate form.
That is a time saver. Did everybody hear what Riley says? So we already saw that created a 0. We know by the remainder theorem, right, that this is in fact a factor of the polynomial, and so we don't have to go and check 1. We already know that -1 is going to work, and that'll be enough to chunk it down from a cubic to a quadratic by dividing out this linear factor. Riley, I want you on my team. That's awesome. That's a time saver. Great work. So let's go ahead and do that. What's my strategy? Well, the algorithm is side times the bottom, right? Side times the bottom is -1, and then add. So -4 minus 1 is -5. Side times the bottom is +5, and then add, and so I get -3. Side times the bottom is, oh, I get 3. Bad with numbers, sorry, thank you. So -2 plus 5 is +3, good. And that's great news because now side times the bottom equals -3, and that's what we wanted, right? We already know that this is going to be a 0 of my numerator, right? Because our direct substitution in the original produced a 0 on top. Thank you, Riley. Now we can go ahead and use, I mean, why do we still have to do this? Because we needed these coefficients for my quadratic so that I could continue in my rewrite of the numerator. So I know that x plus 1 is a factor. Right? I know that x plus 1 is a factor. I'm going to keep my limit as x approaches -1. I'm going to rewrite that numerator, however, as x plus 1 times 1x squared minus 5x plus 3 all over the original x plus 1. Because we're evaluating a limit where we're not concerned with the value of the expression at x equals -1, in fact x doesn't equal -1, we can cancel out these common factors. Go gadget term, and we're left with the limit as x approaches -1 of x squared minus 5x plus 3. Is my x value of concern in the domain of the original expression? Not the original. Is it in the domain of the rewritten? Yes! So we can evaluate through direct substitution, which was our goal in the first place. That's what we wanted to be able to do. So I'll go ahead and jump inside. -1 quantity squared is +1. I can drop the limit for the first time. Plus 5 plus 3. And I'm getting 1 plus 5 is 6 plus 3 is 9. I got 9. Anybody else get 9? You got 9? Yes! That's great news, you guys. So that was a whirlwind, right? That was a whirlwind of a problem, but lots of good stuff in there, including the potential irrational root theorem, the remainder theorem, the zero factor theorem, some synthetic substitution, and lastly, right, our factorization, the result of the limit evaluation through substitution. What question you guys have on today's vote? Sammy? Okay. So as we get closer, right, to our Friday, we're going to have a little bit of time to practice and review. But first, we're going to go ahead and take a look at some function behavior. So at this time, if you take out your OTL number 4, we'll get you credit for that in Infinite Campus. At this time, please give yourself credit for those you completed out of 21. Divide, enter, multiply by 2. After making sure that your Infinite Canvas score is boxed in pencil, nice and big on top of the page, and your heading is complete, first and last, 2A and number 4, go ahead and pass from the back to the front. Front rows, make sure they're facing the same direction, please. I appreciate your help, you guys. I appreciate your help each and every day, ladies and gentlemen. Let's go ahead and get after a discussion. So today will be a short discussion together as a whole group, and then you'll have an opportunity to work quietly with a classmate as you consider the review problems. We've got a couple different sections that the review problems are from as you work and prepare for your unit test. So it's a 100-point test, 2 parts, non-calculator and calculator allowed, as is the case with the actual AP exam. So each of our tests will be practiced in a way for the actual AP exam by breaking up into a non-calculator portion and a calculator allowed portion. You'll have the full 90 minutes to complete. It's likely that you won't need the entire time, but you will have it, so you want to make sure that you're coming ready to go. When the bell rings at the beginning, we'll get started right away, okay? So make sure that you're ready to go right at the beginning. It's not a time then to ask questions, right, or review. You're not going to have that time on Friday. You want to make sure you take care of all that stuff before Friday, so that you have the full 90-minute block. Does that make sense? Awesome. Let's go ahead and practice some with our limits and how we can use limits to determine function behavior. So given the following information, let's sketch a graph of f. We'll label any horizontal and vertical asymptotes with their equations. And so as I consider this description, I know that f of 0 equals 2, and so on our page, we can handle that. That piece of information would show up as an ordered pair. What would the ordered pair f of 0 equals 2 be, right? What would that ordered pair be? Savannah?
2.
Oh, what would the ordered pair be? If f of 0 equals 2, right, what can I plot on my graph? 0, 2, good, thank you. Let's go ahead and consider the limit of f of x as x approaches negative infinity. And that's the same as the limit of f of x as x approaches positive infinity, and that equals 1. So if the limit of f of x as x approaches infinity is a constant, some y value, what feature does that point to on the graph? What feature does that point to on the graph? Anna?
A vertical asymptote.
A vertical asymptote certainly involves infinity. The question is it a vertical asymptote when x goes to infinity and that equals a constant? Or is it a vertical asymptote when x goes to a constant and the limit goes to infinity? See what I'm saying?
Mm-hmm.
Allie?
So like for the first one, it would be a horizontal asymptote, because like as x goes to infinity, you have to like draw closer to a y value.
Ah, so as you look to the far ends of the graph, that's my end behavior. If that's a constant, then we're talking horizontal asymptote. Let's go ahead and throw that in our picture. I'm going to use this dashed line to signal horizontal asymptote. And it looks like as x goes to positive infinity or to negative infinity, my function values go to 1. Good, thank you. The limit as x approaches negative 2 from the left-hand side is the same as the limit of f of x as x approaches 2 from the right-hand side, and that goes to infinity. So then this feature, right, this feature must be a vertical asymptote. Let's put that in at negative 2, and again at positive 2. And now let's go ahead and see if we can't draw a picture here. So we want our function values to go to 1 as we look to the far ends of the graph. We want our function values to shoot towards infinity as x approaches negative 2 from the left. So that would be what here? And as it goes to 2 from the right, so that would be like here. And x goes to negative, I'm sorry, f goes to negative infinity as x goes to negative 2 from the right. So negative 2 from the right would be like here. And f goes to negative infinity as x goes to 2 from the left, so that'd be like here. Oh gosh. And what are we missing? We need that horizontal asymptote end behavior. So we need to level out. So can we connect these such that we have a picture that satisfies all these things? I think we can. I'm thinking a swoop like this then. So like a swoop like this. A swoop like this. I know you're thinking right now, swoop, very technical term. A swoop. Swoop. There it is. And what about this middle? Well, remember, it's okay to cross the horizontal asymptote. In fact, you can cross the horizontal asymptote an infinite number of times. Such is the case with like our dampening harmonic function. It models the behavior of a shock absorber on a car. We go back and forth across that equilibrium point, right, an infinite number of times, and yet each time the displacement gets less and less and less. Right? If you think of a sinusoid going out towards infinity but shrinking, you cross the horizontal asymptote and yet you're still approaching that particular y value. It's okay to cross horizontal asymptote in the middle. You just don't want to be crossing it then out towards the end unless you're dealing with that dampening function. So I think we could do something like this and still satisfy each of those things, right? So we've drawn a picture that satisfies each of those things. Awesome. Let's take a look at another. Given a function definition, for what values of x does f have an infinite discontinuity versus for what values of x does f have a removable discontinuity? Well, in each of these cases, my function is undefined. And so if there's particular values of x for which the original graph is undefined, then I know I've got possibility for infinite discontinuity or removal. And so if I set my denominator equal to 0, are there any values of x for which the function is undefined? Absolutely. We could solve this and get x squared equals 9, so x equals plus or minus 3 are my problem areas. Now I know last year, right? You did your factorization right away and you saw what factors appear on top or on bottom, right? And if you can cross out that factor, then it must have, if you could remove that factor, right, then it must have been contributed to a removable discontinuity. And if you can't remove the factor, then it's there for the long haul. It must be determined the location of vertical asymptote, and that's all true. It's just that there's a quicker way in terms of plugging that in and generating those undefined fractions. One is 0 over 0, right? That's our one where the limit exists, the overall limit exists. And the other one was a constant over 0, and that's where we're dealing with an infinite limit, and that's a vertical asymptote. And so we can get these without having to do our factorization first. We could still just plug in 3 and see what we get. At x equals 3, I get 3 squared is 9, plus 2 times 3 is 6, minus 15 is 0, all over 0. So at x equals 3, which feature do I expect to see? The infinite or the removable? Removable. And so I'm thinking at x equals 3, I get the removable. Let's see about x equals negative 3. Direct substitution yields negative 3 squared is 9, minus 6, minus 15, all over 0. I'm getting 3 minus 15 is negative 12, a constant over 0. Is this indeterminate? No. Is this going to give me a value of the limit? No. This is infinite, right? This is infinite, and it must be a vertical asymptote. That signals the presence of an infinite discontinuity at x equals negative 3. Now, you could still factor that top, factor the bottom, and see which factor occurs both on numerator and denominator. Then that factor would be responsible for the presence of the removable discontinuity if you could remove it, or if you could not remove it, then it would be responsible for the infinite discontinuity. Both are acceptable. It's just that plugging in and getting these quotients that we've been talking about with limits is going to set us up better for our subsequent AP discussion with L'Hopital's rule and rates of change. And so that's why I encourage you to do it. Do it this way. You can still factor, certainly as a means for verification, right? Okay. What then will we get for our limit of f of x as x approaches infinity? Well, recall, as x approaches infinity, right, we're talking about end behavior. And so I can construct my EBM, my end behavior model, and then analyze that for my overall value of the limit. So let's go ahead and see. As x approaches infinity, I can construct an end behavior model. For us, the end behavior model will be given by the quotient of the dominant terms. And so make sure you grab your signs. I get x squared over x squared for my quotient of the dominant terms, and that's just 1. So it looks like I have a horizontal asymptote. As x goes to infinity, f of x goes to 1. Now let's consider the limit of f of x as x approaches 3. Have more space? I don't. In order to do this, I will complete my factorization. And so I know that that gave me, as x approaches 3, I know that gave me 0 over 0, an indeterminate form. So I'm going to go ahead and factor the top, factor the bottom, and evaluate the limit. So my top goes to, let's factor. Factoring's fun. Factor first to fail. What are you getting for your binomial factors on top there? Go ahead and tell the class when I call on you. Be ready. When we factor that, what are we getting on top? Emily?
Negative 3, well, x minus 3 and x plus 5.
I'm down. I'm getting x minus 3 and x plus 5. On the bottom, then I'll do x minus 3 and x plus 3. And because we're evaluating a limit where x doesn't equal 3, we can cross out the x minus 3 and the x minus 3 and try again. I'm getting x plus 5 over x plus 3. And that is, my x value of concern 3 is in the domain of that. So through direct substitution, I can evaluate this limit algebraically, and I no longer have to write the limit right now. I get 3 plus 5 over 3 plus 3. That in turn is 8/6 or 4/3. What we do? Awesome. As x approaches -3, right? As x approaches -3, but from the left-hand side, I know as x approaches 3, that's infinite. So to determine which it is, I can do a sign test, right? I can do a sign test. Let's go ahead and do my sign test now. So what can I do? I'll go ahead and plug my sign test into x plus 5 and x plus 3, and I would be getting -3 from the left. Those are values like -3.1, right? -3.1, -3.01. That'll ensure that the sign of this factor is still positive, right? -3.1 plus 5 is going to be positive. Over -3.1, -3.01, -3.001 plus 3 ensures that the sign of the denominator factor will be what? Slightly negative. Positive over negative, overall, it's going to give me the negative that I need for my limit. Negative infinity is what I'm getting. Let's perform the same test, the sign test, but now let's do it as x approaches -3 from the right. These would be values like -2.9, -2.99. This factor will remain positive. However, -2.9 plus 3 is going to be slightly positive. So I get positive over positive is positive infinity. I'm dying to see how we did. And so let's go ahead and take a look at our emulator. All right, let's see how we did. So we want to see what quantity, I'm just going to do the original, x squared plus 2x minus 15, closed quantity over x squared minus 9, closed quantity, we don't want 22x, flag, how's that? She, okay, and we want zoom 6, and we'll see. So here we come. As x goes to -3, but from the left we went to negative infinity. As x goes to -3, but from the right we went to positive infinity. And if I were to trace, and put in 3, would I get 4/3? No, the function's undefined there. But if I scooch just a little bit to the right, I should be getting something that's close to 4/3, like 1.32 is close to 1.33333 is 4/3. If I went a little bit to the left, 1.331, so that's close to 1.33333 is 4/3. So through inspection, and we could certainly change our window or table settings to get closer and closer, but we're seeing that we're correct. All right, so I'm confident then that we got it all, and I'll go ahead and box that. All right, what questions do you have on this example for F? All right, then one to go. We'll carefully sketch a graph of the function P. That's a piecewise defined function. Non-calculator, then we'll go ahead and check with our grapher. Recall, we can construct a picture using our graphing calculator by using the test, the math test, and the relational symbols greater than, less than, and so on and so forth. And you're going to be expected to do a performance task on your test Friday. You'll have to come up and show me the graph of some piecewise defined function, right? And you won't be able to ask me how to make it. That's what I'll be testing. So let's make sure that we're comfortable doing it algebraically or with our calculator. Let's go ahead and sketch a graph of P algebraically. So what do? Well, we'll break it up into different pieces. I'll go ahead and do a red piece. For this first piece, I'll do in red. I know that this first piece, x plus 4, is just the graph of a line with slope 1 and y-intercept 4. So if I were to make that piece, I would plot there, 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 and so on. However, I only want that rule to produce a picture when I'm looking to the left of or equal to -1. So I'm not going to connect my line forever. I'm only going to start filling in points here and to the left. Next, I'll do a blue piece. This middle section in blue is going to behave exactly like the upside down parabola, whose y-intercept is 4, and vertex is 0, 4. And so it looks to me like 0, 4 would fill in this point. I'd be an upside down parabola, out 1, down 1, out 2, down 4, out 3, down 9, because my growth factor, k, is just 1, so it behaves exactly like out 2, down 4, out 2, down 4, exactly like a upside down parabola, right, in our parent function. However, it only applies when I'm in between -1 and +1. And so I'm going to have an open circle on this +1. I would have an open circle at x equals -1, but it's already been filled in. It's already been filled in with the red point. I better do this. And one piece to go. This final piece we'll do in green. It's going to behave exactly like a line with y-intercept 2 and slope -1. However, it's only going to apply if I look to the right of or equal to +1. So it looks like we only want this piece. All right. As we look back at our picture, for what values of x is the function discontinuous? So for what values of x is the function discontinuous, and what parts of the definition fail? All right, so I'm looking, and we can see our big discontinuity there, right? What type of discontinuity is that, Preston? A step discontinuity, good. So we have a step discontinuity at x equals 1. And what parts of the definition fail? Recall for continuity from our bell work that the overall limit of p of x as x approaches c must equal the value p of c. Well, at x equals 1, is my function undefined? No, it's defined. It's just defined to be 1, right? At x equals 1, does the overall limit exist? No. How come? Brandon?
Because the left limit and the right limit do not match. The left limit being equal to 3 and the right limit being equal to 1.
Absolutely. So the overall limit of p of x as x approaches 1 does not exist, right? So the left-hand limit doesn't match the right-hand limit. Awesome. All right, guys, let's verify. Let's practice. This is a good practice, too. So you're going to have to do this on your test. So I want my first piece to be given by x plus 4, but only when, and so remember, I divide that last term by quantity, and I'll do my restriction. Everybody try it to make sure you're comfortable on your test. We'll go math, test. So second math is test. Less than or equal to is the 6th option. -1, everybody do it. My middle piece is given by 4 minus x squared, but only when x is between -1 and 1. How am I going to do that? Well, I don't know that it'll let me do a string. I might have to do an and. So I'm going to do x is, someone try a string. Right? Someone try -1 is less than x is less than 1 and see if it works. Riley, did it work?
Yeah, but I kind of figured out a different way to write the inequalities. You could just you put the inequality in parentheses and you multiply it by the other term, and then instead of divide. And if it's more than 1, you just do that for both. You split up the inequality into like x is greater than -1 and x is less than 1.
Did you do 2 parentheses?
Yeah.
Okay. I'm gonna try that.
Do a series.
I'm gonna try that. So I want to do greater than -1. So I've got second test. I'm gonna do greater than. So that's 3. -1. I was gonna do and. I wanted to do the and to see if that worked. And then I'll do that way. I'm gonna try this and see if that works because I think it's kind of money. And x is less than 1. So I don't know if that's gonna work with the parentheses. I want to check right now before I go further. Oh,
Oh,
bam! That's very sweet. All right, what am I missing? So I got the and with second test logic, and I pulled that and. Riley just did parentheses with each restriction, no operation in between.
No.
I mean, okay, awesome. And 2 minus x. Next time I'll have to do the right colors. 2 minus x, and that's only going to apply when x is greater than or equal to 1. All right, I'm pretty excited about this. If you can't tell.
bring on the money.
That's pretty sweet. Basically, love math. Love the emulator. That's pretty neat. So, are you comfortable entering that, producing a picture by yourself? Great. Then guess what, you guys? You're going to have the remainder of the time to work quietly with a classmate, right, or in a small group on your review assignment. That is OTL number 5. It's included here on your printout. Annika?
I'm just wondering, like, I'm having some issues.
Oh, okay. Let me come there individually after I get them going, okay? I want you to know that these come from, right? These come from the review problems and the test problems in your book. Answers to the review questions are in the textbook. Answers to the test questions, right? Those are posted on Moodle. You want to review and practice your algebraic techniques for calculating limits because those are not adequately reflected in those review problems. I added a special star bullet for you. Make sure you look back over OTL 2 where you did all those algebraic techniques, right? OTL 2 had all those algebraic techniques. That's not included in the review problems here, so make sure you do that on your own as a means to prepare for your test. Does that make sense? Sophia?
Will there be questions about the intermediate criteria?
Yep. Absolutely. So we need to make sure that we can apply the intermediate value theorem. You may have to write some things. And so think about what prerequisites, all right, are necessary in order to apply the intermediate value theorem. And we wrote down several things that give you a template, Jake, for what I'd be expecting to see on a test or a quiz. Excellent. I'll go ahead and pause the recording here then. And you can use the rest of the time wisely, and then Annika, I'll take a look at your calculator.
There's 100 points, but like how many questions? It's not 100 questions, right? Okay, good.